Hi everyone. So in this video, we're going to take a quick detour and talk about data science. We're going to introduce what data science is, talk about how lists and loops are relevant for data processing, and then look at a couple common patterns that we see in our loops that can help us write this type of program. So to get started, let's talk about data science. So data science is the field of computer science that deals with getting some input data and then using a variety of mathematical and statistical tools to process all of that input data and arrive at some actionable conclusion. So this is really valuable for science, doing research. You need to be able to analyze research experimental data. It's also very valuable for marketing and industry to be able to look at advertisements and see, oh, was this money well spent? Or look at inventory and make predictions about sales. All of that is going to use data science programs to power those conclusions. And this is a very, very big field for computer scientists. It's a up-and-coming field, or not even up-and-coming, a well-established field of programming. And so it is a very good thing to learn about and get a bit of practice with as you are learning computer science. So the great thing about this is the math is whatever level of complexity it will be. It can be something as simple as a mean, median, and mode measure of tendency. It can be complicated statistics, but the actual programming part of data science uses just those tools that we've looked at already, lists and loops. All of these data science programs are going to start with a large group of input data. Usually if it's, say, experimental data, you don't just have one measurement, you have a series of these all identical types of information sitting in one group, which, if you remember our discussion of lists, sounds like something that's perfect for a list. And then the actual meat of one of these data analytical programs is going to be taking the information out of that list and transforming it however we need to, converting it into other types or into other formats, somehow aggregating it down, merging it, summarizing it into some final result. And what this means is that there's sort of two different levels that we think about these data science programs. On the higher, more abstract level, we think about them in terms of changes that are happening to all of the data all at once, saying, oh, well, I have a list of measurements. I need to turn that into a list of numbers, and then I need to add all those numbers together, get some final summary. But in terms of the actual mechanics of working with lists, you might remember from our discussion of loops that we don't actually work with lists generally through the entire list at once. Instead, we have to process these items one at a time. And so the analogy I like to use for this type of program is sort of like a conveyor belt. On one side here, we've got all of our input data sitting in a list, and the meat of our program is going to be a loop that pulls out single items one at a time from this list, and then applies whatever changes we need to do to format it, to convert it, or get some derived value from it using math. And then eventually we either stuff all of those outputs into a second list of results, or we aggregate them down into one final summary result. And so what I want to do in the rest of this video is look at a couple patterns when we're writing this type of program that we see again and again and again, because it can help you stop and classify when you've got a big complicated question and break it down into a couple simple, well-defined steps so that you can memorize just a couple recipes for your program and immediately start typing them before you're even finished thinking. So that is our goal And the first pattern I want to look at is a plain transformation. So a transformation, or what's sometimes called a map, is just the act of taking a list of one type of data and then applying the same change to each item in that list so that we end with a different type of data. So a great example of this would be, let's say I've got a record of a bunch of times that measurements were taken. The way that that might be written in the input file might be a string of text that says 6:30 and then 6:37 and then 7:15. And that's really valuable for a human looking at that. But if we want to do any type of math, that's not a great representation. There's no formula that takes in a colon in hours and minutes. So what my transformation might be is a step that converts each one of those strings of text as my input and turns it into a number of minutes since some time, maybe since the start of the experiment. So that I start with a list with strings like 6:30 and 6:37, and at the end of my map, I have a list of numbers like 2 minutes from the start, 5 minutes from the start, which will be much easier to process and work with. So the way that we write this type of pattern with a loop is if I've got some list original, I'm going to take each item in that list and loop over it and say, hey, that item, apply whatever my transformation is to it. And that might be something as simple as, hey, I want to add 1 to each of these. Maybe I'm transforming from grades to grades that have had 10 points added to each of them. So it's just the new item would be item plus 10. But it could also be something that I have to describe with a function. I could write a function to say, oh, I'm taking the square root and adding 4 and then dividing by 2. Or write a function that looks at the string and splits it on the colon and gets the hour part and the minute part and converts that into a number. However you are doing this transformation, the first thing in that loop that is doing this processing of your list is going to be to apply that transformation and get the new item. And then you're going to add that new item to your list of results. Because remember, with a transformation, we have a list as an input, and then we have a list of a different type of thing as output. And this step of the conveyor belt is like each thing is going through, and the function that sits here in the middle is converting it from the input type to the output type. So this is a nice, neat way to change your list into something that's easier to work with. But sometimes we need to go a step further than that, because with our transformations, if I get 10 things in, I always get 10 things out. And especially as you get deeper into data science, it's very common that you don't just have 10 things, but you might have 3 trillion Facebook posts or 2 billion sales over the 50 years this company has existed. And in that case, there's another pattern that's really helpful. And that pattern is a filter. So much like our transformation, a filter is going to be built around a for loop. But unlike with that transformation, with a filter, we start and end with exactly the same type of data. You know, in my little conveyor belt analogy here, I had green squares in and I'm getting green squares out after this code runs. What the filter does is it allows us to throw out items that don't match a particular condition. So here in my little image that I've constructed to make it physical, we've got this thing that is checking, hey, are these things on this belt actually green squares? If it's a different color square or it's a different shape, those are all getting filtered out. And so I know at the end of this, I've only got just that type. Some real world examples of this might be if I've got my input file is all of the grades for all of my students, maybe my filter is I want to figure out how one student is doing. So I filter and only get the grades from that person. All of the grades from other students get removed from my list. And so at the end of my for loop, I end up with a much smaller, more focused list that either cleans up mistakes in the data or gives me just the data relevant for a specific question that I want to answer. In this case, how is that one student doing? So filtering, the way we would write any processing like this is we've got that same exact loop where we have some original list of things and we're checking each one sequentially. But this time, we're going to put an if statement directly inside of that for loop. And that if statement is going to tell us what is the condition that we're checking. Yes, it gets to stay on the belt. No, it gets dropped out. It gets removed. And if we are doing the same thing we did for our first example, adding these things onto a new list, then what happens inside the if statement is the ones that have met our condition get added to the new list. If it didn't meet the condition, then we skip that, and so they won't end up in that final result. This is also a good moment to mention that with a lot of these data processing tools, there tend to be two ways that we can approach them. Either we can do what we've done in these examples of creating a new list and moving things from the first list to the second, or even making a copy. But there is another way where we can change one list in place. This works better in scripting languages like Python, where you can play fast and loose with lists as you're changing them. But if we were to do that, we could do that exact same pattern like our filter here by instead saying if not our condition, if our condition is not met, then our original list removed that same item. We might need to then check which position, do it with that I for a range, but this would allow us to just have one list and shrink it down if that is a preferable way to think about it for you. But both of these will be roughly the same speed unless you're getting down to either very, very, very large data or very small differences in time. So it's best to do whatever makes it most readable for you. But that is our idea of filtering, is just a pattern for loops that allows us to shrink a list to just part of that list based on some condition. The last pattern I want to look at is aggregation. So if you remember aggregation from a math class, aggregation is the process of summarizing and condensing a list of items down into one single final result. This is sometimes called folding or reducing in computer science, but whatever term you use for it, the thing that we get in is a list of items all the same, our input data, and the thing that we get out is one single aggregate result. It is not a list anymore, which means aggregation, if it happens at all in your data processing, it has to be the very last step, because your conveyor belt can't continue once you've aggregated your data. There's only one number or one string or one object of data left. And so we can't keep looping because there's nothing to loop over anymore. However, that said, aggregates tend to be some of the most useful pieces because it's what makes very large data sets comprehensible. Good examples of aggregates are things like sums and averages, where we could say, I've got, going with that grading example again, a whole list of grades, that is how you've performed on each assignment in a class. But the thing you probably care about is what grade did I get for the whole class? So you're taking a list of inputs, but you only want one final result. Perhaps a weighted average of all of those assignments that calculates a final score. Another great example of an aggregate is something like a highest or lowest, saying, oh, well, I've got a whole bunch of times of people's performance on a swimming race, let's say. I want to figure out what was the best time, what is the record. I have a whole list coming in, but I want just one, the one single highest result. So if I want to do this type of data processing, what that loop is going to look like is before the loop starts, I need some variable holding that final result, and it needs to be equal to whatever the default value is that makes sense for your aggregate. And this is what makes aggregates trickier than our other types. All of our other types of data processing, you could just start with an empty list and head right on your way. But now you have to think about when I merge each result in, because that's what we're going to do in an aggregate. We're going to loop, again, the exact same loop. And this time we will merge the results so far with the next item, and that becomes our new intermediate result. We need to think, well, what is the identity of that? If you remember the identity property from math, if you're doing addition, for example, your default value will be 0 because 0 represents nothing being added. It doesn't affect merging all of your list items together. But if we were doing something like multiplying them all together, multiplying by 0, suddenly, no matter what your input data was, your result is 0 because anything times 0 is 0. So in that case, we would want to use 1. And it gets even more complicated as you start doing more sophisticated aggregates, as you start doing trickier merge processes here. You have to think about, well, what is really the value that will never mess up my final result if I'm taking a highest or a lowest? You know, if I'm taking a lowest, maybe I start with a very, very high number. If I'm taking the highest, I start with a very, very low number so that it never shows up as the answer. But however you do it, all you're going to do is take that result and apply it to that next item, merge them two together. And just like with our transformation, this can be as simple as an operator like addition, or it could be something you describe in a whole function that says, oh, well, here's how you extract that weighted component and apply it to the number, or this is how we merge these two things together. Maybe they're both strings and you have to add a comma in between them and a space or something. But to give you a concrete example of this, say I had my list of scores and I wanted that average, that running example we've been using. For that, our result would be 0 as the default value, because for an average, we have to do this in 2 steps. Step 1 is add all of our components together. So for our loop, all we're going to do is take the sum of all of these numbers. So for each item in my inputs, my sum equals, that should be sum equals sum plus item, to add each one of these things into a total score. Once I've got my total score, to take the average, I divide by the number there are, and that gives me a pure unweighted average. So each thing gets an equal amount. This brings up a good point with aggregates, is that some require a bit of post-processing, a little bit more polishing after the list is finished. Average is the classic example here because you have the adding part and then the division part, but it applies to a lot of different other types of math you might want to do. Standard deviation, people often compute it in a way where you're taking sums and sums of squares and then doing some stuff at the end. And this is true for a bunch of different processes. But no matter what, that merging step is still going to be the same. You need to figure out what is my sane default value, and then how do I apply that operation each time to what I've looked at so far plus the next thing? And that is our idea of an aggregate, which is our third looping pattern. These are each really valuable tools, but they're most valuable when we combine them together. So in real-life data science problems, it's often necessary to combine filtering and transformations and then some final aggregate into a pipeline of operations that you're applying. You're not just doing one of these. Instead, you're going to do a whole bunch of them, starting with your input list, do some first change, then some second change, maybe aggregate it at the end, get a final result. So you have to combine these steps together. And there are a couple different ways that you can do this. The simplest way is you can just write a for loop for each one of these steps. You can have your for loop that does the first map, and then you get some new list, and then that new list becomes your new original, and you do a filter, you get some third list, and then your third list becomes the thing you use for the aggregate loop, and that works perfectly fine. If you want to be a little bit fancier, if you notice, each of these three looping patterns has the exact same loop. So what you can do is, if you take each one of your steps, you can grab just that body of the loop, just the thing that's indented, and put them one after the next. Say, if I'm doing my transformation first, I've got the item, and it turns into new item. And then on the next line in that same loop, instead of immediately building the new list, I can say, well, if that new item meets my condition, that thing that I've transformed, now immediately do that check. And then inside the if statement, if I wanted to aggregate it, instead of adding to a list again, I could say inside that if statement is where I would do that merge. And this allows us to chain these together. You could even have multiple transformations and then a filter, then another transformation. And each one of those just becomes another line after the next inside your for loop. But the significant thing is, if you've learned about this technique for processing data, when you look at that big, complicated, scary loop, you should still be able to identify a pipeline of changes happening one after the next, each of which is 99% of the time one of these three types of loops that we've looked at, one of these three patterns for data processing. So the last note I have about this is that modern programming languages are increasingly adding special functions that allow us to think about this without even having to write the whole loop. Python, for example, has map and filter and reduce functions that allow you to write just a single line of code where you say, I want to map this list with this function as my transformation step, the transform function that we had from our original here. Whatever name makes sense for the transformation you want to do, you name your function that, and then you just pass it to the map function, and it gives you back the list of results. This is great for keeping things in terms where you can really easily at a glance identify, oh, well, I'm doing this pattern, then that pattern, and keep track of what you're doing to your data from the input to the output, almost keeping you closer to that abstract thinking about working with the entire list all at once. But that said, you don't have to use that. Like we mentioned before, it is just as good to write those separate loops if you find that more readable, especially as you are just starting out getting familiar with programming. But that is something that is out there if you ever do see that. But that is it. That is our introduction to data science. So like I said, this is a big field in computer science. If you are a very data-oriented, analytical person, It is a great thing to explore, but all that it is data science is this process for examining data where we think about a pipeline of sequential transformations that we apply to one of those items at a time. And the goal of this is to boil down a bunch of inputs into an actionable conclusion, either data that's imminently readable or even just a single summary. And as we're doing this type of work, we need to think about how we break down whatever complex questions someone is asking of us into chains of these simple patterns of transformations and filters, and maybe an aggregate at the end to take our list of inputs and turn it into a list of outputs or a final aggregate output. And like we said, there are many different techniques for actually writing this code. You can do it with loops, you can do it with mapping functions, but this concept of a pipeline of changes is universal. No matter which version of the code you're writing, the actual steps that you're doing in the computer remain unchanged. So hopefully this is a useful framing for you for thinking about this type of program. From here, we are going to go back to learning more about other instructions. So look forward to that, and I'll catch you all in the next video.